All right, Sam, what's going on?
We're going to be learning first principles of reinforcement learning. So we're going to be learning about what gradient descent is today.
Cool.
So gradient descent literally means going down a. Imagine we have this hill, and we want to find like what is the very bottom. So it would be like right, and so we're at the top of the hill, and just like logically speaking, we want to go either up or down. I mean, those are the only two options we have. So we go up and we realize, okay, we're going in the wrong direction because we went up and we went higher. So then we go down and then we're like, oh, wait, we went down and we're at a lower place. That means that like, this is exactly what we want. And so what we actually do is we take the gradient here, just be like the direction of where we're going. And based on the direction of where we're going, do we have better results? So if we have better results, we continue going down to the gradient. So now we're here and then it's continuously going to go down. Again, how big these like steps are is based off of your learning rate. That's like a hyperparameter that you could change. So we go lower and lower and lower, and then eventually we'll like hit the lowest point. Again, this is probably the easiest function to cross over. Now imagine we had something like this. Okay. So the reason that reinforcement learning or just like basic ML feeds or machine learning is difficult is because we get stuck in these local minima really often. So let's just suppose we have like a learning rate that's not, or that's pretty large. So for example, like from like here to here, I hope you see this. So we'll just call this 1 unit. So we're going down 1 unit. Okay, we're going lower. We're going down 1 unit. Okay, we're constantly going down. Everything's doing great. And then we hit like this part. And then if we continue going in the same direction, we're actually going to end up going higher. And so since the learning rate is static, we are just going to go back and forth. Okay, and we're never going to be able to get to this point right here, which is actually the lowest. The way that this is actually fixed is by using stochasticity, which is like where stochastic gradient descent comes from. Whenever you have a lot of training data, you actually have small batches where you basically randomly sample the data, and that will give you some random gradients that don't actually match up to reality. So if you have like, let's just say 5,000 samples training data, every 30 random samples might give you a slightly different gradient, even if it's not true. So realistically, instead of it being following like the exact gradient every single time, it's going to go a little bit lower. And then it's like, okay, maybe I just randomly decide that from my 30 samples that I actually have, it actually might go up. So there's a little bit of randomness going on there. So we should get out of this eventually. Now, robotics, on the other hand, nothing like a simple 2D function. Okay. Robotics works in a very high dimension. So, if you didn't know robotics, the more degrees of freedom you have, the more dimensions you have. It's like, it's exactly the same. So basically, however many joints you have is how many dimensions you need to plot this on. And this becomes really difficult because every single leg and like bar movement does affect how it transforms in the end. So let's just say we had a robot with like 3 degrees of freedom. Okay, so I'm just gonna give a 3-dimensional grid. Not really sure the best at drawing this, but we have a 3D grid, and let's just say we need to find like what's the local minima over here. The actual plot will be like something like this. I'm really bad at 3D, but my point is that the more dimensions you have, the more difficult this is, and the amount of local minima and saddle points that are going to be inside of this like 29-dimensional robot, it's a lot, right? So the only thing we can really do is sample a ton of data, and thankfully IsaacsSim is really good at that. It's able to parallelize lots of matrix multiplication, so it's able to find lots of training points, but working with 29 degrees of freedom is so difficult that we need like millions of training points. But as time goes on, we see that we can get up to 1 million steps a second, and uh, hopefully we'll just be able to stand reinforcement. Now, reinforcement learning is very similar to, well, it is a form of machine learning, right? The only thing that reinforcement learning has is it has an environment. So uh, it has an agent, it has an environment, and then you're typically trying to maximize your rewards rather than minimum. So uh, again, your reward is what you're trying to get the highest. And whenever you're doing something like locomotion, so walking, you're trying to stay stay up, not falling. You usually penalize falling a lot. You usually try to move in the same direction, or in a lot of papers, like the 8th paper, they just decide to have a stable velocity in a certain direction. And the longer you're able to maintain that velocity, the better your locomotion is. So yeah, see you next time.